Good morning, everyone. My name is Abubakar Musa. I'm a data scientist and research and development project manager in industry. Today, I'm going to introduce a work done by me and my colleagues. The presentation is entitled PDM FSA Predictive Maintenance Framework with Full Severity Awareness in Industry 4.0 using machine learning. My presentation will follow this point. First of all, an introduction, then a presentation of related work, followed by a presentation of our proposed solution, then a presentation of performance evaluation, and finally the conclusion. So, the predictive maintenance refer to the ability to predict the need for maintenance of a given asset at a specific future moment in a smart factory. And nowadays, it has a number of use case. For example, in mechanical engineering, in railways, in aviation industry, in automobile industry. Correctly apply, predictive maintenance brings some advantage. For example, it helps to decrease the downtime and also it increase the production. Also, it helps to increase the return on investment and also it helps to decrease the maintenance cost. These are some advantage introduced by predictive maintenance. However, the application of predictive maintenance in a smart factory bring with it a number of challenges. In fact, sensing devices used in a smart factory generate a large amount of data that can be leveraged using machine learning to provide useful information and gain insight into manufacturing processes. In Industry 4.0, it is crucial to establish an accurate model for identifying the potential machine failure and understanding their specific characteristics. In the literature, different ML-based solutions for predictive maintenance have been proposed. Nevertheless, several challenges remain related to the ML implementation, including the quality of the data collected, the resource constraint, and equipment heterogeneity. Therefore, in this work, our objective will be to address the problem of predictive maintenance in a smart factory environment within the context of Industry 4.0 and also to propose the right classifier for predictive maintenance that take into account multiple criteria. Before presenting our solution, let's take a look at the literature. Supervised learning model such as decision tree or random forest and unsupervised learning models such as K-mean have been used in order to provide a solution for predictive maintenance in Industry 4.0. Generally speaking, they have been proposed with the aim of improving the model accuracy. However, they do have their own limitation. This is particularly true with regard to accuracy. On the other hand, it is important to note that none of these solutions have been focused on fault severity. We therefore propose a model that will improve the performance while taking into account the fault severity. Let's take a look of our proposed solution. The main goal of our proposed framework is to provide an efficient machine learning model in order to adaptively predict when it is necessary to perform predictive maintenance in a smart factory according to the severity of equipment malfunction. So the proposed framework involves four steps. First one is data collection. The second one is dataset splitting. The third one is data preparation. And the last one is model training and inference. During the data collection, uh, sensor devices uh, collect data from smart factory equipment, and then during dataset splitting, the data collected are separated based on the type of failure, and during data preparation, different operations are applied. Notably, here we have data cleaning in order to remove missing value. We have a statistical analysis. We have outlier identification and removal. We also have feature engineering. And during model training and inference, we selected a set of machine learning model based on different criteria. We trained them, and also we evaluated them based on different metric, and also we perform validation, and after that we perform inference. In this work, in order to produce the optimal predictive model for predictive maintenance, we considered an ensemble method which encompass four classifiers, notably KNN, SVM, XGBoost, and random forest. And for this ensemble method, we adopted the voting strategy in order to obtain the final prediction. So the voting strategy combine multiple classifier in order to make final prediction based on the weighted average of the individual prediction. On the right hand side of the screen, you will see the pseudocode for the training process of our meta classifier. Let's move to the evaluation of our proposed solution. In order to perform the evaluation of our proposed solution, we considered different metrics. First one is accuracy. The second one is the precision. The third one is F1 score. Then the last one is jamming. The accuracy is simply the degree of agreement between a measured quantity value and a actual quantity value of a measurand. This allows for the assessment of the performance of a model on a given dataset. The precision is a criterion that helps to evaluate the ratio of true positive to the total number of positive predicted by the model. The F1 score refers to the harmonic means of precision and recall. The optimal value of F1 score is 1, whereas the worst value uh, correspond to 0. The J-mean is useful for evaluating the balance between the classification performance in both majority and minority classes. The best value of J-mean is 1 and its worst value is 0. On the screen, you will see three tables showing a comparison of results for predictive model for different type of fault. Overall, we can see that our proposed model perform well compared to the other state of the art model. In order to show how well our proposed voting classifier perform, we plotted these three figures. And this figure represent the 95% confidence interval for the ensemble classifier for the different type of fault. Moreover, we also perform features importance analysis, and the result of that analysis show that our proposed framework can be improved further by reducing the number of future feature during training. To conclude, in this work, we propose an ensemble classifier based on four machine learning models that are widely used in predictive maintenance. And also, we propose an evaluation of our proposed classifier in order to highlight its performance against existing solution. In the future, we plan to reduce the number of features and deploy our proposed solution in order to evaluate the proposed framework in real environment. Moreover, we will also explore techniques such as domain adaptation, transfer learning, and continual learning in order to enhance the model capacity for adapting to new data distribution and mitigate potential bias. Thank you for your attention.